Hello. In this video we will go over an optimization problem. We'll start with this truss system over here, shown here, which has two members, and these are the conditions that we are going to use. All the numbers are defined here. So we have a maximum allowable stress within the two members from which you can form these two stress constraints. And then we have a displacement constraint, which is that the displacement constraint is that the tip should not displace more than delta naught. Okay, so using this condition you can come up with a displacement constraint equation like this. And then finally the objective is to find the area for the members such that the total mass of the structure is minimized. So this is the mass equation over here. So now we have a function that we would like to minimize within three different constraints given. Okay, so let's see how to do the implementation of this in Python. So what we're going to use is the SciPy optimize toolbox, from which you can use the minimize function to minimize your mass function. Okay, so the first step is to define all your constraints as equations. So let's define our mass function over here. So let me run this first, then define mass, and this should return the equation shown here, rho L over here. Now the function can only take one input. So you have to pass, in our case we would like to optimize both area 1 and area 2. So this can be passed as a list or a tuple of two values, and this will show up as a single input to your function. So this will be x, but once inside your function you can unpack the value. So you can say a1 comma a2 equal to x. So this is how you can pass two values into the function and then unpack it inside the function. Then you have the other values which you need to define inside the function as well. Rho equal to 1, L equal to 1, and yeah, I think that's it. That's your mass function. And then for the constraints, you'll have to provide the constraints like this. You can just say, using the keyword argument constraint, you can provide it with constraint. If you have multiple constraints, you can make a list of all the constraints. Each constraint is defined as a dictionary item using curly brackets. It has two key and value pair, which is one is type and the other one is the function. So the type, there are two types. You can either do inequalities or you can do equalities. If you want to learn more about this, you can always go down to optimize.minimize and just press shift tab to open up the help for that function, optimize.minimize. And you can see constraint is mentioned here. If you scroll down, constraint is supposed to be a list of dictionaries, and within the dictionary the fields allowed are type, function, Jacobian, and args. So in type you can either say eq for equality and ineq for inequality. Okay, when you do equality constraint, the equation has to go to 0. When you do inequality constraint, it just has to be non-negative. So you'll have to write your inequality constraint such that the result is non-negative. Okay, so let's start with the first constraint, the stress constraint in 1. Okay, the same thing happens here. You have to just unpack both the numbers. And stress constraint number 1 is 2f divided by area 1 should be less than or equal to sigma. Okay, so in this case you have to rewrite this equation such that it's non-negative or it's positive. Okay, so it's going to be sigma naught minus 2f divided by area 1 should be greater than or equal to 0. So you can just write it over here. Return sigma minus 2 times f divided by area 1. Again, meaning sigma over here. And then finally you have the other condition. You have define and you also have the strain constraint or the displacement constraint. Let's call it. Again, this has to be written as a non-negative function, so you have to move the left-hand side to the right-hand side. So it's going to be sigma naught divided by f minus these two terms. So sigma divided by f minus these two terms. Now that we have all our constraints, let's just try to visualize it before we start the implementation, so we have a better idea of like how the optimization will work. So we could plot out all the mass values within a given range. So let's assume that the area changes from 0 to 30, and then we'll see how the mass of the structure changes. Okay. To do that, you can create a mesh grid and a contour plot. So we'll do x comma y equal to np dot mesh grid between two values. So this is going to be between np dot a range, let's say from 0.1 to 30 with discretization of 0.1. I'll create the grid, and you can then compute the mass at every point. So mass at x comma y. Okay, this will be our z value, and then you can make a plt dot contour plot using all this information. So x comma y comma z. I'll disable the solution now, and this is your mass, and you can put a color bar to see the values, and label this as mass. So as we increase your area, so let's add that as well. plt dot x label is area 1 squared. This is area 2. So as you increase area 1 and area 2, the overall total mass of the structure also increases. Okay, and now let's try to plot our constraints on top of this. To plot your constraint, you can use the following function plt.im_show. This adds an image on top of your the plot shown here. To make it transparent, you can use the command alpha, the keyword argument called alpha. Now what are we trying to plot? We're trying to plot where area 1, we're trying to plot where stress constraint is, we're trying to plot the three constraints. So let's do stress constraint 1, and we said it has to be non-negative. So wherever it's greater than 0, show that part on the plot. Okay, we can do this. So we have to input both the x and y values here as well. So x, y, x is a1 and y is a2. Okay, so we're just trying out different values for a1 and a2, and then just plotting whichever values give a positive result. It's going to show up in your figure over here. Okay. So now you can see it has broken down your figure into two regions. One is less than 1 doesn't meet the condition. The yellow part meets the condition. Okay. But it has messed up with the scale of the graph. To fix this, you need to use the extend command. Extend, and then you need to provide it with the min and max values for your x and y vectors so that it can scale it properly. So now it's at the right scale, so now it's at the right scale, and you can see that stress constraint 1 deals with area 1. So if area 1 is greater than this value shown here, I think it's around 3, it meets this condition over here. Okay, now you can do the same for the other conditions as well. So stress constraint number 2 is going to show up like this. So there is the origin. When you do im_show plots, will be by default at the top corner here. This is 0, 0, so this graph doesn't look right. So So let's flip it. You can just use the command origin equal to lower. Okay, this should make sure the graph, because usually for figures, for images, the starting pixel is here, so this is 0, 0. But when you do a plot, the starting value is here, 0, 0. Okay, so just to make sure they match up, you use the origin command. Okay. So now this looks about right when area is, so it's only acceptable when you're in this yellow region. So this is the yellow region, you will meet both the stress constraint. Now we can also do the same for the strain constraint. And you can see it has added all the three regions. So the only region that you're allowed to be in, area 1 and area 2, the combination that you're allowed to be in is in this yellow region over here. And the optimization algorithm needs to find a value that minimizes area. So as you go up, the mass increases. As you go down, the mass decreases. Yeah. So the best point visually, you can kind of see it somewhere. It should be somewhere here. Roughly a bit less than 10 for both area 1 and area 2. So let's see if our optimization code actually runs and gives us the same result. Okay. So now let's enable the optimization code. It's optimize.minimize. You're minimizing your mass function. You have initial inputs of 1 and 1 for area 1 and area 2. So you're starting somewhere here. And the constraint, right now I have only one constraint defined. So let's define the rest of it. Just copy this one. You have stress constraint 1 and 2, and then the strain constraint. Okay. Now if you run this code, so you can see the best point is when area 1 is 8 and area 2 is 7. So you can also add this to your plot just to confirm that it is in the right spot that we found earlier. So this is going to be, this is stored inside solution under the field X. So you can extract this out. You can say A1 optimum equal to solution dot X, the first value, and A2 is the second value. Okay, then you can add this to your plot. Just say plt.plot and A1 underscore optimum and A2 underscore optimum, the Y value. And this will not show up because it's a single point, so you'll have to add some kind of marker. So you can say 0 to show it as a round marker and B to show it as a blue round marker. Okay, there's just a shortcut to set the marker properties. And just like we guessed, this is the point, this is the optimal point where you have minimized the mass and you also met all the constraints. Okay. Now one quick thing to note, you can see some constraints are overlapping. So for example here, the strain constraint is the dominant one. The stress constraints are actually being overlapped by the strain constraint. So technically you could have found the same answer without even implementing the stress constraint. So had we remove these two, we would still end up with the same points here. Okay, so it's the same numbers, 8.0 and 7.9, just to keep that in mind. But this only gets revealed when you do a plot like this and then compare your position. And that's it. This is how you do optimization in Python. Thank you.